Can y'all see the handout? Okay, sweet. So, okay, cool. So, yes, someone said he goes a lot into bicyclic compounds. Yes, but okay, trust me, Diels Alder isn't that bad. It's actually, in my opinion, great because there is so much to this reaction. It's actually awful. But as far as Orgo 2 goes, you have to know the bare minimum. It's amazing. It's wonderful. So that being said, let's get into it. So essentially, Diels Alder is a cycloaddition reaction. And that just means we add multiple things together to make a cyclic compound. And we also call this a 2,4 cycloaddition. And the reason we do that is because 4 electrons are going to merge with 2 electrons, but I'm getting too ahead of myself. We'll get into that in 1 second. I just wanted you to be aware that that is another name for Diels Alder. So, in Diels Alder, we're going to have a molecule like this. We talked about this week. What kind of, I guess, functional group do we have here? A diene, exactly. And then someone said, can this also be called a pericyclic reaction? Yes. I think pericyclic might be a more specific term, but as far as you guys need to know, yeah, it's pretty much the same. So, yes, we are going to react a diene with another double bond or triple bond. And so essentially, I'm going to zoom in really close, but I'll zoom back out. So the diene is going to be the nucleophile. And it is going to plop some its electrons and form a bond, right? But this carbon already has 4 bonds, so its double bond is going to, bam, right there. And so now that this carbon is getting another bond formed, this double bond has to move over here. So all of our electrons pretty much went in a big circle. And I will highlight the new bonds we made in blue. So those are the new bonds we formed with the electrons. And this was our original diene structure. And then this was the double bond we reacted it with. Any questions so far? Okay, so no one said anything yet. You can still ask if you have a question. But essentially now we are going to give these things names. So all the pieces of this puzzle are going to have names. We already know that this is the diene because that's just what it is. And we're going to call the other reactant a Dienophile. It's a funky name, but that's okay. And so now we're actually going to go ahead and kind of compare and contrast the two. I'm not sure if I gave you guys a table. I did. So I'll just go ahead and write in the table for you guys so you know what I'm talking about. So as we mentioned, the diene is doing the attacking, so it would be the nucleophile. Interesting. Someone raised their hand. That's cool. Do you have a question? If you do, you can unmute and ask.
Oh, yes. I thought I was already unmuted. I'm sorry. Anyway, so the Dienophile, that's That's the one with the COH, right? That's the compound with the COH, the double bond and COH. I just want to make sure
Yes,
that I have.
exactly. So
Okay,
I
thank you.
will actually
It'll always look like that?
no. So I'll explain exactly what to look for in the Dioelectrophile in like 1 second,
Oh, okay.
and then if you still have a question, feel free to ask again. Okay?
Thank you.
You're welcome. Also, I love that as soon as the hand raising option was a thing, everyone was just like, "What is that?" and started clicking. That's me. Okay, sorry, I got distracted by that. So as we said, the diene is the nucleophile, which would then make the Dioelectrophile our electrophile. I'm just going to turn that on because I get weird emails. Okay, so as we said, our diene is a diene. So we're literally just going to say it has to be a diene. So it must be conjugated. However, the Dioelectrophile is actually going to be any alkene or alkyne. And an alkene is a double bond, and an alkyne is a triple bond. So another thing that's important to know, and you can make sense of it, but it's one of those things you just kind of have to remember. So the diene always has to be in S-cis conformation. In order to react. And the Dioelectrophile has to maintain its configuration. And what I mean by maintain configuration is if you started out with a trans alkene, you'll end up with a trans product. If you start with a cis alkene, you'll end up with a cis product. So and if you don't know exactly what that means, I'll do a bunch of examples in a second, just so everyone's clear. And then the last thing, I actually want you guys to logic out a little bit. So if we have the nucleophile and the electrophile, we know that the nucleophile to attack needs electrons, and the electrophile wants to have very little electron density, so it can have a delta plus, so it's more reactive, right? So we have things called electron donating groups and electron withdrawing groups. Before I even go into what those things are, just using the names electron donating versus electron withdrawing, which one do you think the diene will prefer? A donating group or a withdrawing group? Okay, so we're getting pretty much a 50-50 split, and that's to be expected. Essentially, the nucleophile wants to get more electron density, so we're going to want electron donating groups, because if we had electron withdrawing groups, you would be a worse nucleophile, because you would have less electrons to attack with. And don't feel discouraged if you got that wrong, because I didn't even tell you what these groups are yet, but I just wanted to see what you guys thought. So as I mentioned, we want electron donating groups, and I'm going to call that EDG. And the reason for this is because they give more electrons, and that makes it a better nucleophile. And for the electrophile, we have the exact opposite. So we want electron withdrawing groups. And the reason for that is they want to pull away electrons. you get a more delta plus. And that means you can better accept electrons. I shorthanded that, so that's like not even like a real English sentence, but I hope you guys understand what I meant by that. So
Wait, can you repeat that one more time, please?
yes. So to recap, the nucleophile is the diene, so it must be a conjugated diene. It must be in the S-cis conformation, which means both double bonds are pointing the same direction. And it wants to have electron donating groups because it wants to have a more negative charge. It wants to have more electrons, and therefore it can be a better nucleophile. The electrophile, on the other hand, is the dienophile, and it can be any alkene or alkyne, so aka any double or triple bond. And it doesn't matter what configuration it is in to begin with, it just has to maintain that configuration. And it wants electron withdrawing groups because the electron withdrawing groups pull away electron density, giving it a more powerful delta plus, which makes it easier to accept electrons, making it more electrophile.
When you say that they want electron withdrawing groups, do you mean they want to react with those kinds of groups?
Good question. So no, that just means we want those kind of groups attached. So for example, if we go up here, this is the diene, right? So this is all you actually need for the reaction, and this is the dienophile. This group and this group are just substituents that are attached that either help or slow down the reaction. So for example, we'll talk about why this is in a moment, but this is an electron donating group, and this is an electron withdrawing group. So we have these groups attached, again, because if the electron donating is on the diene and the withdrawing group is on the dienophile, it makes the reaction much, much faster. And so now we're actually going to talk in depth about these kind of groups. So I'm going to scroll down. And I made you guys a nice table. I don't know if it's helpful because the boxes are kind of small, but you guys can let me know. So the electron donating group, which I'm going to call our EDGs, are basically the ones that have lone pairs. That's a huge show that something is a donating group, because lone pairs are usually going to donate through resonance. Another example is R groups. But before I draw in the R groups, let me just draw out a couple examples. So we have, excuse me, my hand is touching it. NH2, OH, all right, and so just before I go on to anything else, this squiggly right here just means that this is where it's attaching to our group. So for example, if this was my diene, and I was putting this electron donating group onto it, it would attach from the squiggly line to our nitrogen, and then we would have these two hydrogens. That's another one of those things that they always just do in organic chemistry, but they don't really tell you what it means. So, all right. So lone pairs I'm underlining because any group that has a lone pair is going to be a strong electron donating group. And it's important that you know that it's strong because in the next chapter that we talk about, you're going to have to rate the strengths of the withdrawing versus donating groups. So while it's not insanely important for this exam, just keep in mind this is a strong electron donating group. The weak electron donating groups are our R groups. And an R group is essentially any carbon chain. So like a methyl, an ethyl, a propyl, whatever. And so this, again, I will say is a weak electron donating group. And the reason there's a difference between the strong and weak groups is because the strong groups will donate by resonance, while the weak groups will donate by electronic effects. And someone asked in the chat, like, what is a strong electron donating group? If that didn't answer your question, let me know. And then an example for a weak electron donating group is just any R chain. So it would look something like that. And if we wanted specifics, we could have an ethyl group. I'm so sorry. Or like any other R group. One other thing I want to mention is, let's say we have a methyl versus a tert-butyl group. Which one is going to be more donating? The methyl or the tert-butyl? Ooh, we're getting some mixed answers. And then someone also asked, like, what do we mean bioelectronic effects? So you might remember back in NMR, I know forever ago, a terrible time that we try not to remember, we talked about, or not even just, we talked about this last chapter. So when we were talking about the difference between the aldehyde and the methyl, right? And the carboxylic acid. So the carboxylic acid donates by resonance, right? And then here we had these electronic effects where the methyl was donating electrons, right? And yes, hyperconjugation also comes into play. But so what I mean by electronic effects is that these carbon groups are going to donate a little bit of electron density through hyperconjugation and other electronic effects, versus the oxygen will do this through resonance. Sorry, my pen is refusing to write. And then someone also asked, what's an example of a strong electron donating group? And so I probably was not as clear as I should have been. All of these are strong electron donating groups. There we go. I organized it and maybe it looks a little bit better now. So lone pairs are the strong electron donating groups, and that is all of these examples. R groups are the weak electron donating groups, and they are weak because they only donate by electronic effects, while lone pairs will donate through resonance.
I'm a little bit confused. The structures you drew for the lone pairs, doesn't it contain an R group?
Not all of them, but yes. So it does have an R group, but that's not the important part. So this oxygen is what is actually attaching to the molecule, and that has this lone pair, and that's going to be the bulk of your effect because that's what's like right on the molecule. So you might have a little bit of extra push from the R group, but we primarily care about this oxygen right here.
Okay, so the lone pairs are usually on the electronegative atoms, so and then the R groups just contain carbons.
Exactly, yes.
Okay. All right.
And then one other thing I forgot to mention, electron donating groups also contain negative charges. So anytime you see a negative charged group charged group attached to the diene, you know that that's going to be electron donating. Those don't come up as much, which is why I forgot about it for a second, but that's an option. So if you ever see a negative charge, that's probably electron donating group. On the flip side, we have electron withdrawing group, and if electron donating was negative, we know that this is going to be positively charged. So anything that's positively charged is going to withdraw electrons. And I don't know why I gave you guys boxes instead of just an open space to write. So it's whatever. But anything with a carbonyl like this, CF3, any halogen, and the nitrile, anything like that is going to be withdrawing. And someone asked, oh, I forgot to finish up my explanation. I'm so sorry. I'm all over the place. So the reason I drew this out is to tell you which one of these two was more donating. And the one with the more carbons will be more donating. And the reason is, like we talked about here, we had more donating effects when there were two methyls versus just one. So the same kind of logic applies here. This is a smaller chain than this one. This one has more carbons to donate electrons, so this one will be more strongly donating. I'm sorry, I forgot to do that and I had to come back to it. Does that make sense? If not, I'll be happy to repeat it. Okay, it seems like people are saying it's okay. So back to electron withdrawing groups. So there are a bunch, and I'm pretty sure he gives you like a million groups on the PowerPoint. But these are the most common ones in this chapter. We are going to talk about a few more next chapter, but that's not relevant for this exam, so I don't want to confuse you guys with it. Any questions, comments, or concerns about electron donating versus withdrawing groups?
Is there anything else in the electron withdrawing groups, or is that all that it covers, basically?
Are there any what? I'm sorry.
Any other points that you would want to talk about for electron withdrawing groups, or that is all that it covers?
That's pretty much all that it covers. Anything that has like really electronegative atoms, except for nitrogen and oxygen because those have our lone pairs. Anything that's supercharged, anything with halogens, anything with a carbonyl, things like that. One thing, actually, I will point this out now, just so I can put it in the chart. So there's a difference between this and this. And the difference is which side the squiggle is on, right? So if we have an ester and the carbonyl side is attached to the molecule such that it looks like this, that is an electron withdrawing group, because the carbonyl is going to take all the electrons for itself. It will not donate at all. However, if we attached it the other way, now excuse me, I don't know why I have the hiccups. So now these electrons will actually primarily go this way to donate here, but they will also donate towards the system. If this looks really weird, don't bother drawing it out like that, because I know the arrows can get confusing. Just know that in this case, where it's attached at the carbonyl, it acts as an electron withdrawing group. But in the case where it is attached to the oxygen, it works as an electron donating group. This is where people get kind of confused. If you don't see what I'm talking about, just look it over one more time, and after we actually draw the mechanism, think about it logically, why you think it makes sense where the electrons go. And so someone asked, so the carbonyl needs to be directly attached with the double bond in order to be an electron withdrawing group? Yes, that is true. So without further ado, okay, so I'll actually ask you guys for your opinion. Do you want to keep working on all these diene versus dienophile problems, or do you want an example of the actual mechanism and then come back to this stuff later? And you guys can either say like mechanism or practice problems. Okay, cool. So usually this stuff is on the next exam, so I don't have to like rush through it. It's usually the first stuff we start out with, but it's fine. It's cool. We will finish covering this on Monday, and I will post a video of all this Diels Alder stuff like at once in order, so it's not as confusing. But I have to jump around a little bit today because it's Friday and we don't have that much time. So without further ado, let's do a mechanism. And I kind of put these in a random order. So I'm going to be nice and do an easier one first, and then we're going to work to the harder ones, even though that's not exactly the order this is in. So that being said, we're going to start with this one right here. And I'm going to zoom in. And first thing we have to look at, we have A and B. Which one is the dienophile? B, perfect. And so that means by default, that one is the diene. And you would also know that just because there's two double bonds, diene, right? So next thing we have to check is this the right conformation? So is the diene an S-cis conformation? Yes, cool. So conformation is checked off. Next thing, we're going to look at donating versus withdrawing groups. So does the diene have any groups attached to it? Ooh, we got a 50-50 again, and this one is a trick question. So I'm very impressed that some people said yes. The this actually counts as an R group, right? Because it's attached to the double bonds. So this is a weak donating group. So I'm just going to write in a different color, electron donating group. And so what about these groups? First of all, tell me what functional groups those are in the chat. It's very important that you guys can tell what these condensed formula functional groups are. So what do y'all think? Even if you get it wrong, that's okay. I just want you to try. Cool. So people are saying aldehyde, and that is correct. And that would mean it is an electron withdrawing group. So now I'm going to redraw this so that it's like facing the right direction. So this is what it will look like. And I want you guys to note, this is different than the first example we did because what's different about the diene? It's cyclic. It's a ring. Exactly. And so this makes it a little bit weird because we know we have to make a ring system, but we already have one, right? And so a lot of people will say, oh, well, this carbon is in the way, so these electrons can't go in a circle anymore, so that would be no reaction. And I definitely see where those people come from, but instead of letting it kind of be in the way, we're actually just going to go ahead and take the tip and flip it upwards like this. And like if you were taking a piece of paper and you literally just folded it up like that. So we're going to pretend this is now pointing upwards. It's out of the plane. It's out of our way. And so now we actually move these electrons around. And before you start drawing arrows or anything, I want you to go ahead and connect the diene to the double bond. And I have kind of a cheat way to do that. So when you're doing the diene, you're going to number it, and you're going to start from one end of it, and you're going to go 1, 2, 3, 4. So 1 and 4 are always on the open sides. So, I'm sorry. So like here, right? And then you're going to name the Nucleophile, or yeah, name it, I guess, A and B. And A should always match up to 1, and 4 should always match up to B. You are never going to add this way. Do you guys see what I mean and like what the difference is between the way these are oriented versus how these are oriented? Waiting for a couple yeses in the chat. Okay, cool. So once these are properly oriented, all you got to do is move the electrons around, right? And so now we know, I'm going to erase this so I have a little bit more room. So we know that we are going to make a 6-membered ring because that's just how Diels Alder goes. And we know that that is going to come from the diene. We made these 2 bonds, and this comes from the Nucleophile. And we know that we have a new double bond here, right? But we had a whole bunch of substituents. So let me go ahead for you guys and number. So this was 1, 2, 3, 4. This was A and this was B. So off of A and B, we have an aldehyde on each. So it will look like this. Or I could have drawn it the other way where the second aldehyde was pointing down, but I have a hiccup again. I have a reason for why it's pointed upwards. Just trust me for a second. And then the way we draw this tip in is we said that it is pointed upwards, right? So I'm going to try my best to draw in 3D, and we get this. So what we have to deal with now is how this versus these substituents are oriented. So we already said that this was an S-cis conformation, good to go. But what did we say about the configuration of the diene? The Dienophile. It has to stay the same, exactly. So it was cis here or Z, and so that means they have to either be both pointed up or both pointed down. And we actually have special names for when it's pointed up versus when it's pointed down. While I draw the other answer, does anyone know what those names are? Someone said axial and equatorial. That is a good answer, but not exactly what I meant. So we have endo and exo products. Exactly. So the endo product is when it's pointing into the system, and the exo product is when it's pointing out of the system. And you guys might think it's counterintuitive, but when we say the system, we're talking about the double bond. So in this case, it's pointing away from the double bond, so we're going to call that the exo product. And then when it's pointing down, I haven't done an amazing job at drawing it because it's kind of hard to draw in 2D, but these double bonds are pointing downwards. They're pointing into the system, so we call that endo. And so now, which product do you think is preferred? And that'll be the last thing we talk about for today because I know it's 1:50. Ooh, cool. So we have a 50-50 split. Perfect. Exactly what I wanted. So, 2 reasons why one is preferred. So this is, oh my God, I'm so sorry. So this pointing up here causes steric hindrance. So that's one thing we don't like. But also, when these double bonds point down, we actually get something called, you don't have to know this, but it's called pi stacking or a really great hyperconjugation. And this will actually interact with these groups to form this extra stability. So when the double bonds point down into the system, aka endo, it's going to interact with this double bond to stabilize the ring. And so the endo product is the preferred one about 90% of the time. So I know I threw a lot of information at you guys. Again, we're going to go through this again on Monday and all that jazz. So ask, what do you need to know how to do for the exam? So yes, you need to do the product, but yes, you need to know how to get the product, But for this one, you also have to kind of know the mechanism. Because one, it doesn't take long. 2, it's not very long. And 3, it makes more sense if you can draw it out this way. If you can just look at it and see the product without even thinking about it, cool. That's super awesome. I have gotten to that point now, but it's really difficult your first time around. So I would say draw it out. Yes, we can for sure go through the mechanism. I will do it on Monday for sure, like about 100 times. But if you want, I will stay a couple more minutes and do it again with you now.
Can you explain how you need to orient the dying that way, like on its side with the tip pointed towards the Dionophile or whatever it's called?
Yes, of course. So I'm going to go back up here for that. And so we're going to use this example again. And this is actually, I'll make it even simpler. This is the simplest possible Diels Alder reaction we can ever have. And so I like to call this the open side and this the closed side, because this is the single bond that's holding them together, so it's closed. And I like to think that the open side is where you start counting, so 1, 2, 3, 4. And the Dionophile is pretty much just A and B, it doesn't matter. In reality, in higher level chemistry, there's a bajillion things that go into how you orient these things and how exactly the arrow mechanism works. For this class, doesn't matter. All you need to know is that if he gives you like this drawn like that, you just need to be able to say that, no, we would have to turn this around. I don't know what happened, excuse me. We would have to turn it around and reorient it so it's facing that way. And then we know that these sides then have to line up. Does that make a little bit more sense?
Yes, so we have to point the open side always towards the Dionophile?
Yep.
Okay.
Even if it's not technically open, like in this case, if you just think about it strictly as the dying part of it, you can kind of tell that this is still the open side.
So will all dienes have like the similar bases? That's how you found out that the peak was the R group?
Exactly.
Okay. Cool.
So
Thank you.
every single example, this is the base, and anything else added to it is just an extra group. And then someone asked, am I going to only post the SI sessions? No. So I have decided every topic that we do, I'm also going to record like a short video of me just explaining it. Because I know it's annoying to watch like a 50-something minute video just to get like one little thing. And sometimes there's interruptions or, you know, I ask a lot of questions. So if you just want to hear the explanation without any interruptions or anything, that's why I post those. I've just been really bad at recording them this week because it's been a heck of a week. So I filmed a couple today, so I'll put those up at some point this weekend. But yeah.
I just have one question.
Go for it.
So how did you know, like, how to, like, draw the product?
Great question. So in Diels Alder, we're essentially always going to make a 5-membered ring. That's the whole thing for Diels Alder. So what I did is I already knew that my diene looks like this, and my Dionophile looks like this. So my screen is frozen. I don't know if it looks frozen to you guys, but okay, here we go. So we have the diene, which has this like 4-carbon basic structure, and our Dionophile, which has this 2-carbon basic structure. So that's what I drew in here in purple. And then I knew that these electrons were forming new bonds, so I connected those new bonds here. And then the substituents are what are kind of weird. If we have a ring structure already, the tip is always going to point up. That's just a rule. The tip will always flap upward. So what you really have to kind of then figure out is the way these are pointing. And we know that they have to be pointing the same direction as one another because they were cis here, or Z. And we just need to figure out, are they pointing up or down? And then we can figure out whether they're pointing up or down because we want them as close to this double bond as possible. And as we can see, when it's pointing down, it's closer to this double bond than when it's pointing up because then it's going away. Plus, you can also think of it as this is sterically hindered versus this is not.
So we're forming both products, like Exo and Endo.
Yes, but this is your major product. So you're going to have like 99% this and like 1% this.
Oh, okay.
Cool. Any other questions? These have all been really, really great questions.
I'm sorry, can you point out the five-membered point of the ring? I'm just getting confused because you said in these reactions you always make a five-membered ring.
6. So we're always going to make a 6-membered ring.
6.
Yeah, and I will highlight that in red. So it will always make this basic ring, and then everything else will just be substituents.
How did you know to like put the tip, like the thing in black?
Great point, or great question. So the reason we put that is because we started with a cyclic diene. So anytime your diene is already in a ring, you're going to have a tip pointing up. And let's say this was a 6-membered ring and you had 2 carbons here, both of those carbons would go up.
So you only make a 6-membered ring if you start with a ring?
So no. Like if we look at this example up here, we still made our basic 6-membered ring here, but there's no like point anywhere, right? And that's because this was not a ring.
So the tip will be everything that's not including the 4 carbons, right?
Exactly. So
The original.
for example, if we have a 5-membered ring, we get, again, our regular 6-membered ring plus 1 carbon in the tip structure. If we had a 6-membered ring like this, we would get the same 6-membered ring structure, but now we have a really ugly thing like this, where we have 2 carbons that are pointing up.
So the tip always goes where 1 and 4, like the carbon 1 and 4 are?
Exactly.
Oh, okay, I see.
It's going to be a bridge between 1 and 4. You're absolutely right.
So depending on the substituents, that's how you'll get the bicyclic structures?
Exactly.
Okay, cool. Thank you.
You're welcome. You guys are doing so great. I get so excited. Oh, you guys are too sweet. Oh, I forgot to send the link. I mean, it's Friday. You've already heard my spiel like 18 million times, but I'll send the link anyway because my supervisors want me to. So yeah, it's Academic Support Week. You know the drill. If you want to be nice to one of the SI leaders or tutors, especially Jared, because he's amazing. He covered my tutoring hours this week because I had some emergency stuff going on. So if you want to give him a nice little note, that would be much appreciated. And yeah, I'll just stay on for another minute or so.
And then the way you put the aldehydes like that, just from the molecular formula, you just knew that it was an aldehyde and you had to draw it in like, right?
Exactly, yeah. So we know that COH is like is the condensed version of an aldehyde. So we knew that was a substituent. And then deciding up or down had to do with sterics.
Okay, so we have to memorize the condensed formulas basically for a lot of these molecules.
Pretty much, yeah. But for the most part, he will give you like it in picture form. The only thing you really have to know for these examples is like COH equals aldehyde. CO2H is carboxylic acid. CO2 CH3 is an ester, things like that. Those are the kind of things that kind of expects you guys to just know off the top of your head.
Okay.
But yeah. And yes, Diels Alder should be the last topic you have to know for the exam, because he said he's only going up through chapter 13.
Okay, another thing I wanted to ask you, I think this was like 2 weeks ago or a week ago. You were doing chapter 12, and there was like the last part of it, the practice problems, I think it was, that you didn't finish.
Yeah.
I don't know when, if we're gonna do that or we're just gonna do that in the review.
So we are for sure going to cover that because it's very, very important. We are going to cover it on Monday, but I am also going to post a video on it this weekend because it's really important. I don't want.
Okay, wait. You said because you said on Monday we're gonna do. Okay, so on Monday we're gonna finish this part of chapter 13 or last part of chapter 12.
Well, no, I want you guys to do the chapter 8 for sure. So we're going to do that first, and then spend the rest of the session doing 13, and then also spend Wednesdays. I'm so sorry. Session doing this, and also we're going to cover everything from 11 to 13 during the exam review on Tuesday.
Okay, good. Okay, great. Thanks.
You're welcome.
Sorry, I just have 2 more questions. Okay, so when he asks what the product is for this reaction, he's only be talking about the major product, right? Like, will we see both products or just the major?
So I guess he could ask you what are all the possible products, but if he just says like, what is the product? He means major product, and this is your answer. So in real life, you're definitely going to see both, but it's going to be like 99% this, 1% this. But usually he'll clarify and he'll say like, what is the major product, or which is the one that's made primarily, or something like that.
Okay, because I know Saint Germain used to ask like for the major, and then other questions asked for the minor. I wasn't sure how he was going to question that.
Mm-hmm. He will 95% of the time ask for just the major product, but if he wants something else, he'll specify it.
Okay, and again, Endo is the one with the the groups pointing down like farthest away from each other because they're less sterically hindered.
Yes,
correct?
Also because it interacts with this double bond.
Also, you said because it interacts with the double
This
bond?
double bond.
Okay. Okay, it's because it's closest to that double bond.
Mm-hmm.
Oh, okay. Okay. So whatever group, whenever it's closest to that double bond, that's where, okay.
Mm-hmm.
All right. Thank you.
You're welcome.
Your exam review session on Tuesday, is that going to be just you, or you and Katrina are going to split it up kind of like what you did in the videos?
We're going to split it up. We're going to do it differently than in the videos because the videos were a whole thing. And so it was like 90% me talking and like she didn't get much time to talk. So we're just going to split it up like 50-50. The first hour is going to be like one person explaining chapter 11 and 12, and then the other person explaining 13. And then we're going to spend the second hour just doing practice problems. And that'll be 50-50 too. I just don't know how we're going to split it up.
Okay, great. Thank you so much.
You're welcome. I'll stay on for like maybe another minute. But yeah, I hope you guys all have a really, really great day and a really great weekend. Relax a little bit. Chill. I went to the beach the other day. It was great. Do something fun. Let me exit. Okay. You're welcome. Bye-bye.